All right, time to get started. Ooh, let me get rid of this light. Okay, when I give out the quiz, what would really be great for me is if everyone sits in a line. So it's every other seat in a line. So starting with, say, this side, we'll have the first seat, the third seat, the fifth, the seventh, etc. Can you do that for me? Because last time it was all zigzaggy and it's difficult.
It hurt your brain.
It hurt, yeah. And I'm always like, I always feel so under the gun when I'm giving out the quiz. Some people aren't going to get this right away. My anxiety goes like up to here. So just be less anxious. That'd be nice, you know. I know you think maybe you're anxious about a quiz, but believe it or not, I'm anxious too. So anyway, all right. So we are working our way through this activity, the activities for chapter 3, and we are up to this one. And I started to do this one way, but I decided to tell you there are 2 ways to do this problem where you're given a certain mass of a compound. In this case, you're given 8.5 grams of sodium phosphate, and you are asked to find the mass of any of the elements. And in particular, in this problem, you're asked to find the number of grams of sodium in that 8.5 grams of sodium phosphate. So there's 2 ways you could approach this problem. And the first way would be to find the percent by mass of the sodium, which I already showed you how to do in Na3PO4. And then, this is actually way A. And secondly, to take that percent of the mass, which is the 8.5 in this case. So if you do it this way, what you have to do is start by finding the percent sodium. So that means when you're trying to find the percent of an element in a compound, what you have to do, as I said last time, is you have to calculate the molar mass of the compound. And then, and as you do that molar mass, you have 3 sodiums in the compound. You have 1 phosphorus and 4 oxygens. So this is 3 times the molar mass of sodium from the periodic table. Okay, that gives you 68.97 grams. This one's pretty simple because it's just 1. And of 4 oxygens at 16 gives you 64. And then you add all this up and you get 163.94 grams. By the way, somebody corrected me. There were at least 1 or 2 gotchas from last time that nobody came up to get. So, all right, well, you have to come up and get them. That's your responsibility. I'm not going to chase you with a gotcha. I hate giving gotcha. No, that's not true. All right, so the mass of sodium here was 68.97. So if I want to find, I'm going to find the percent sodium, that's 68.97 grams divided by 163.94 grams times 100. And that comes out to 42.07%. And now what I could do is just take 42.07% of the 8.5 grams. 42.07% of 8.5 grams. Honestly, every time I do a problem like this, I think of my dad. Because when I was in like middle school learning about percents, he told me percent is hundredths and of means multiply. So it's 0.4207 times 8.5. That's the problem. Of course, most of you would have no trouble with that. And you end up with 3.6 grams. Anyway, that's the answer. And that's grams of sodium. So that's the one way to do it. The second way is something I've already shown you. And if you look back, let's see, it was, oh, I didn't write it down. Oh, it's like activity 2, number 7. It's the second number 6. Remember, there was number 6 and there was another 6. So I changed that 6 to a 7. D. It was a special problem. And so what you can do is you could start, and I actually started this last time. I started it. See, you start with the grams of sodium phosphate. You go to moles of sodium phosphate, yes, by using the molar mass. So now if I did my multiplication here, I would have moles of Na3PO4 as my grams cancels. Then I would use the mole ratio. So it would be 3 moles of sodium per 1 mole of Na3PO4. So that's my mole ratio. That will cancel moles. Another thing I want to point out, that you're really all beginners, okay? And people are tempted to just write 1 mole on top here instead of moles of sodium phosphate. And people are tempted to write 3 moles to 1 mole without labeling it. But, you know, at this stage in the game, you really should label it, because you don't really know what you're talking about if you haven't labeled it. Okay, and then the next step would be to convert the grams of sodium to moles by using the molar mass of sodium. See, if you don't put the label, you don't know if it's canceling right. So now when you do the multiplication here at the end, you will get 3.6 grams. So this is the grams to moles to moles to grams method. Why do I call it that? Grams of compound to moles of compound. If you stopped here, you would have moles of the compound. If you did your math here, this 8.5 times 3 divided by this, you would have the moles of sodium. And over here, you now have grams of sodium. Thing's already given me a problem. I don't know why. I don't know why it's doing that. It's really annoying. You have to stop this recording. Okay. We'll see how long I can keep this up. Okay. So I'll probably cut and paste that here before I post it, so it'll be on the posted notes. Okay, this is a very simple example. If you're given the mass percent of an element in a compound, or of all the elements in the compound, find the mass of that element present in a particular mass of compound. That's a mouthful to say the general type of problem it is, but they want you here to find, it tells you that copper fluoride is 37.42% fluoride by mass, fluorine by mass. Use that percentage to calculate the mass of fluorine in this grams of the compound. So it's what? It's like the opposite. No, it's actually like the second half of this one here, where we took the percent. Yeah, it's not really the opposite. So 37.42% of 55.5 grams. So it's 0.3742 times 55.5. And so it comes out to 20.8. Okay, so that's that. All right. So I want to move on to a slightly different topic. You know, up to now, I've been talking about pure compounds. So up to now, I've been talking about pure compounds, also of elements. You know, I've talked about ionic and molecular compounds. We've done examples with mole calculations with both types of compounds. But many times in this course, especially in the lab when we get into the lab, but we do a lot of it in lecture as well. We don't work with everything pure all the time. A lot of times we work with solutions, okay? And remember, let's remember what a solution is. So does anybody remember what a solution is? Like, how is it defined? It's a certain type of mixture. Yes, it's a homogeneous mixture. And that means that the solute, remember what a solute is. You have a solute and you have a solvent. The solute is the thing that's present in a smaller amount. So we call it like the minority component, which simply means it's present in a smaller amount. And the solvent is like the majority component, which is present in a larger amount. Okay, and a homogeneous mixture of the solute and the solvent simply means that every single part of that solution has the same amount of solute and solvent. It's completely uniform when you have a solution. In this course, in Chem 103, we really pretty much exclusively, how do you spell exclusively? Deal with aqueous solutions. What does that mean? Yes, that means dissolved in water. So that's really all I need to talk about here. All right. So things like salt and sugar dissolve in water. The reason why they dissolve in water, because not everything dissolves in water. If I took a piece of chalk and crumbled it up and tried to dissolve that in water, it would just sit on the bottom. That would be an inhomogeneous mixture, would not be a solution. The reason why things dissolve in water has to do with attractions of those molecules to water molecules. That's not a topic for Chem 103. That's actually a pretty big topic in Chem 104, but we're not Chem 104, so we don't have to learn about that right now. But I wanted to mention it, that it has to do with attractions. The more attracted molecules are to water, the more easily they will dissolve in water. It makes sense, right? So for now, I want to say we're just going to really do the basics. And right now, today, what we're going to learn about is what we need to know to study reactions in solution. And so we need to talk about concentration. Okay, so concentration. Then when a solute dissolves, a chemist will need to know how much is dissolved. It needs to quantify the amount of solute that's dissolved. So the concentration refers to the amount of solute in a certain amount of solvent. Or in a certain volume of the solution. And that's what we are talking about today. And the end of today, actually. And so the most common unit that we use is called molarity. A molarity is a unit of concentration. We give it the symbol N. And molarity is the moles of solute per liter of solution. Okay. And so its units are moles per liter. And a lot of times we talk about the volume in liters as being V sub L. You'll see that in various books. So I want to give you an example. If we take, for example, so here I'm going to talk about making a solution of 29.2 grams of sodium chloride dissolved in water, so that the total volume
is 2 liters. Okay, so the question is, what is the concentration? What is the molarity of the sodium chloride? And molarity, we give the symbol capital M. What is the molarity of NaCl in this solution? So the first thing you have to do is you have to get the moles, right? Because molarity is moles per liter. So we'll have to take this 29.2 grams of NaCl. We will have to use the molar mass of sodium chloride, which I'll give you, 58.44 grams per mole. So that's, I'll put that 58.44 grams on the bottom in order to be able to cancel my grams, okay? So this comes out to, I put some nice numbers in there. This comes out to 0.500 moles of NaCl. If you put 0.5 on a piece of paper, that's wrong. It's really 0.500. There are 3 significant figs here, okay? And there are 4 here. So you should keep 3. 1, 2, 3, okay? All right, now that's not it. That's just the moles of NaCl. Now the molarity is the moles per liter. So it's just 0.5 divided by 2 liters. And so you could see that's 0.250 molar. So we say that's a 0.250 molar solution. Now, how would you make this solution is another question. So you go in the lab, there's all kinds of flasks, right? We have beakers, look like this, sort of. We have Erlenmeyers, which look kind of like this. And then we have something called, it's a very funny looking flask, and it's even funnier the way I drew it because it's not really to scale, but that's all right. So it's called a volumetric flask. And it has a little line on it, okay? Okay, and these come in all shapes and sizes. You could get 50 milliliters, you can have 500 milliliters, 100 milliliters, 1 liter, 2 liters. These volumetric flasks are what you use to prepare solutions. So you might ask, well, why does it have that narrow neck? What is the purpose of that? And the purpose of it is, if you're going to make a little mistake with how far you fill it, you'd rather it was a very narrow neck so that your mistake isn't really amplified. If you fill to, say, a mark over here, and you know the meniscus is huge, you have this, the top of a surface dips in the middle. It's very hard to tell very hard to tell if it's actually on the line. Here, it's actually, if I blow this up, looks like this, and you could really tell if this is the liquid. It kind of dips in the middle, okay? And we call that a meniscus. And it's, yeah, if that meniscus is right on the line, that's what we want in a volumetric flask. It's easy to see the meniscus. And because it's narrow, when you make a mistake, it's not a disaster if it's a 0.5 millimeter off, okay? Even though really, if you're working in a careful lab, you should use a little dropper and make sure you get that meniscus perfectly right. So what do? You would weigh out the NaCl. And in this environment, we usually use a weigh boat. Weigh boat is literally a little plastic holder that looks kind of, doesn't really look like a boat, but it's got sides, you know, it's like a little raft, you know. It's not. Anyway, you have this little weigh boat. And so you would weigh the stuff inside the weigh boat. So that's the first thing. The second thing, you would transfer the NaCl to the volumetric flask. And in this case, of course, you would pick a 2-liter volumetric flask. That's pretty big. It's probably about this whatever. Anyway, you've got this big 2-liter volumetric flask, and you've put your sodium chloride. It's down here now, okay? From the weigh boat, and ends up down here. Then the third thing you do is you add distilled water to the mark. This is the mark, okay? And that means you add it so that the meniscus looks like this, that the bottom of the meniscus is right on that line, okay? Next, you stopper the flask, and then you invert it completely upside down. Invert and mix. In other words, you go upside down, like with this thing. 1, 2, 3, and you do that 10 times. Okay, and that's it. Take your stopper out and use your solution. All right, if you just kind of go like this, you know, it's not going to really be mixed. So do it the right way. All right, we learned it here first. All right, anyway. All right. Okay, so that's how you do it. I also want to tell you that you don't always have to make solutions out of solids. You know, liquids can also dissolve in water. So if you turn to chapter 3, activity 4, the first example down here. So we're going to find the molarity of a solution that has 25 grams. This is ethanol. So another way to write, so the reason I write it this way is because structure is like this. You don't have to know this, but I just want to tell you. So you could see that this part here, there's 2 C's and there's 5 H's attached to those 2 C's. C2H5, and then there's another O attached to an H. This makes it an alcohol. So that's one way of writing the formula, but you would also write it as C2H6O. All right. You would combine this H with the other H's. So you could write it either way. The molar mass I gave here is a little, I'm going to use a more precise molar mass. Okay, and so now I'd like you to do this. Find the molarity of a solution that has 25 grams of ethanol with this molar mass and the total volume of 500 milliliters. And there's one thing you have to do in this problem I didn't show you before. Remember, molarity is moles over liters, and this is given in milliliters. So you're going to have to convert that to liters before you divide the moles by the liters. Okay, so what I do, of course, is I move the decimal point. 1, 2, 3. So it'd be 0.500 liters. Okay, if you're not comfortable with doing that, you can always do it this way. Okay, you get the same answer. All right, so just to work on that one. I'll just come around if you have a question. If you finish that and you want to get started, you can try the next one, which is a little different. I'll go over the next one. I'll go over this one too. Go with the gram to mole conversion. Greater than 2H5OH.
add up 5 plus 1, that would be 6. But I gave you the mole. And you will divide that by the volume of liters. Get the molarity that you're asked to find. Any questions?
Okay, so did you get this 0.543 moles of ethanol? I got 9. So molarity is moles per liter, 0.543 moles divided by 0.500 liters, or 1.09 moles per liter, but we would write it more simply as 1.9 molar. Okay. All right, so that's one type of problem that you could be asked, you need to know how to do. But another kind of problem is, yes, question? So, you have 46.0 grams on the thing. It's 0.07. I corrected it. It should be, I just made it a little more precise. So if you use 47.0, you still have 3 sig figs. It was slightly off. It really should have been 46.1, right? If it's 0.07. So maybe you got a slightly different answer. Yeah. What'd you get? I got 1.1. Right, but 1.10 with still 3 sig figs. So I used 40. Yeah, I don't know. I'm not gonna, that's not the kind of thing that I'm very sensitive to when I grade anyway. If somebody rounded differently or something. I can't go too crazy. All right. So the next type of problem would be like, what if you're asked, like let's say you get a job at a biotech company. It could, lots of our students go on to various jobs in industry, and you're working at a biotech company. It's your first day, and you're asked to make, so they tell you, make 500 milliliters of a 0.250 molar solution. That's my abbreviation for solution of phosphoric acid. Okay, that's your job. But they're not going to tell you how much to weigh out. because they all assume that you know. Okay, so how do you figure out how much phosphoric acid that you're going to need to weigh out? So what you need to do is you're going to use the volume and the molarity to find the moles of the phosphoric acid that you need. Okay, and the second thing is, then you will convert those moles to grams. Okay, so here's the part we don't know how to do yet. Use volume and molarity to find moles. So we know that molarity is moles per liter, okay? So that means that molarity multiplied by liters gives you moles, okay? And you could remember that. Or you could use the wonderful dimensional analysis method where you start with the volume in liters and then you say, how can I put the molarity in this parentheses so that liters cancels? And you'll say, okay, I'm told it's 0.250 molar. What does that mean? It means 0.250 moles per liter. That's what it means. So you would go, okay, 0.250 moles per 1 liter. And you could see that liters cancels. So that multiplying the molarity times the volume gives you the moles. Okay, and that would give you 0.125 moles of phosphoric acid. And then you would just take the 0.125 moles of it's called H3PO4. And I'm just going to tell you what the molar mass is. And the molar mass is 97.994 gram. This is the molar mass of phosphoric acid, H3PO4, grams per 1 mole. And now you multiply this out, you get 12.2 grams. Okay, but you could also, do it all at once. 0.5 liters, 0.250 moles per liter, 97.994 grams per mole. And you cancel liters, you cancel moles, and you'll end up with the same answer. I encourage you, if you're comfortable with it, to do it like this with successive parentheses, just because it's easier. And you don't have as much rounding. You had to round, I have to round in the middle here. Luckily, it was, it was exactly 0.125. So I didn't have any round off error. But anyway, it's not that important to worry about that now. Okay. So how about you do number 2? How many moles of NaCl are in 25 milliliters of a 0.15 molar solution? So here you're again given the volume and you're given the molarity and you're asked to calculate the moles. So it's just the molarity times the volume. But what do you have to do to the volume first? Right, you've got to convert this to liters. So how many liters is 25 milliliters? Because you move the decimal point, 1, 2, and 3, okay? So then it's simply 0.15, actually that's 0.0250 liters, 0.15 moles per liter. And it's really just multiplication here. You get 3.75 times 10 to the minus 3, which you only should keep 2 sig figs, okay? But if I asked you how many grams So the answer to this would be 3.8 times 10 to the minus 3 moles of NaCl. But if you're going on to do another calculation, you should keep an extra sig fig. Okay. So to prepare 25 milliliters of a 0.15 molar solution of NaCl, you would need this much sodium chloride. This is molar. So it's moles per liter, molarity. It's not just moles, it's moles per liter. It's a concentration unit. Tells you how much is dissolved in a given amount of water or a given amount of solution. Okay.
Kind of separated and trying the other.
Okay, so that's how you would prepare some of these solutions. But sometimes, and this is quite often, sometimes you've already made a solution that's pretty concentrated, pretty strong concentration, a high molarity. So very often you have to take a solution you've already made and you want to prepare some other solution of the same stuff that's more dilute, right? That's a lower concentration. And we have to do something, we say, we're going to make a dilution. So sometimes you start with a sort of highly concentrated solution, a concentrated solution, meaning it's a large molarity, greater molarity, and need to dilute it. I mean, you don't always want to go to the shelf and pick up the solid and start from solid. In fact, sometimes if you're making a really dilute solution, it might be a very, very tiny amount of solid, and it's hard to weigh precisely a very tiny amount of solid. So the better thing is to start with a more concentrated solution and dilute it to the concentration that you want. So I need to talk about making dilutions. Okay, so how do we make dilutions? So this more concentrated solution, we have a name for it. We call it the stock solution. It's like the one that's sitting on the shelf. Okay, so we take a stock solution and we dilute it. So I gave you a picture of this, I believe, in the back of the same paper we're working on. Is that correct? Okay, so this is how you do it. So here's your flask that you want to make the solution in. And this is a pipette. And this is a burette. And you could use either one of these two, a pipette or a burette is used. You would have the concentrated solution in here, making it dark so it looks concentrated. And then you would put a certain amount of it. So this green solution here is representing the stock solution that you've put in there. And then you add water up to the mark of the volumetric flask for the volume you want to make. And then you could see that this color here is a bit lighter than this dark color here because it's more diluted, it's less concentrated. So if it's colored, it will be less dark. You know, most of the time we make solutions that are clear. So it's not going to give you any hint that it's been diluted. You have to know what it was you did. All right. But so basically, this is the idea, is you put your stock solution into a volumetric flask, you add water to the mark, You stopper it and you invert it literally 10 times upside down. So don't let go of that stopper, okay? All right, and you'll be doing that, I believe, not next week. Next week, you're going to do the density lab. It's sort of more with, you know, basically giving you some lab experience with measurements. The following week, you're going to do the mouthwash lab where you will make dilutions of a stock solution. Okay, so so here's the thing. So what I have here is a picture of the stock solution that has been added to a volumetric flask on the left, and on the right, after adding water to it. So here's the thing that you have to remember to get to the next part of this, and that is that the number of moles of the solute that's in this stock solution is the same as the number of moles after you add the water. Okay, so the moles of solute does not change when you add water. So you have the same moles of solute in the concentrated solution that is transferred as you have in the diluted solution. Okay, from this, we can get a kind of master equation to solve all of these types of problems. Because what is moles equal to in terms of molarity? Moles is molarity multiplied by volume, right? This is the molarity of the concentrated solution, right? It's darker green, times the volume of the concentrated solution. That's what moles equals. And that will be equal to the molarity of the diluted solution times the volume of the diluted solution. It all starts with the moles being the same. So do you understand that the moles of solute is the same in these two flasks? You know, the moles of what counts here is the thing that's being dissolved. Water doesn't change that. Adding water doesn't change the amount of solute that was added. So and if you believe, and since moles is molarity times volume, okay, we can write this MCVC is MdVd. And this allows us to do all sorts of dilution problems. So I'd like you to go to the next problem, which is number 3. And I'm going to tell you that the hardest part of this problem is figuring out what's being asked for and what are the knowns and labeling each one appropriately, right? Because we have this MD or MCVC is MdVd. That's great. That means we could solve for any one of these things in terms of the others. But what is everything in here? So what's being asked in this problem? Which of these variables are you being asked to find in this problem? What? Yes, that's right. What is the constant? Here it actually asks you right out. What is the concentration of the diluted solution? That would be the molarity of the diluted solution. So MD is what we're after, is what we have to solve for. Okay, so now we have all kinds of other quantities in this problem. So suppose you dilute 55.6 milliliters of 18 molar sulfuric acid to a total volume of 500 mils. So what does that make this total volume here? No. What variable is that going to be? Volume of what? Of the diluted solution. And by the way, it won't be 555 because you're diluting to a total volume of 500, okay? So that means that this 18 molar, right, that is, what is that? Yeah. Well, no. What is the concentration of the diluted solution? That's what we're trying to get. This is the molarity of the concentrated solution. because you're starting with the concentrated. So it's just telling you, suppose you dilute this concentrated solution, right? You get it? Yeah. This must be VC. So we're solving for MD. So I would do it this way. I know most of you would not do it this way, but I cannot do it your way. I think it's terrible. Most of you would do this. I'm just here to tell you, this is what you would do. You would do 18 times 55.6 equals X times 500. And then you manipulate these numbers and make mistakes all over the place. But here it's not so hard. You're just dividing by 500. So it's not so bad. You could do it your way here. That's a very good question. And the answer is no. The reason is because, yes, somebody asked a very good question here. What if this volume is in milliliters and not in liters? It's okay as long as they're both in milliliters, because then your units are the same on both sides. So it works out. Well, the way I would solve this problem is I would solve this equation for MD by dividing both sides by VD. So I would have MD is MCVC over VD, and it would be exactly the same, 18 molar, except I would write it, 18 molar times 55.6 milliliters over 500 milliliters. My units would cancel, and I would end up with 2 molar. Okay. And what does 2 molar mean exactly? 2 moles per liter, or 2 moles per liter. Now I'm going to show you a chemistry joke. Where is it? That's not it. Maybe that's it. Damn it. What happened to my chemistry joke? Oh, I lost it. Didn't you see it at the beginning of class? It was showing. Oh, I'm so disappointed. Oh. Oh, I'm looking at all of them. That's where we are. No, it's all right. I'm going to find it. I have it. I can't get it without my chemistry joke. Now I built it up. It's really not that funny, but now we're waiting for it. So it's going to be a real disappointment. You could see my lovely filing system. Oh. All right, here's a joke. Somebody laughed. Yeah, I mean, they're drinking champagne. You know, if you're listening to the recording, I don't know if this is sharing because that's a new thing, but it's showing 2 little moles in a liter. Okay, well, enough of that. So, so I'd like you to try to do activity 4, number 4. Which I don't have either. Oh, well. Something got spaced out here. It's not it. Well, you have activity 4, number 4, so you can go ahead and look at it. So again, you're just trying to identify what all the players are and use your MDVD is MCVC.
There's lots of ways to make things. That's why you have to figure out. I'm just gonna go out this I'm telling you, this kind of problem is very tricky.
And you have to look at it and you have to, first of all, what is a stock solution? Is that going to be the dilute solution or the concentrated solution? Yeah, this is this one you take off the shelf that you have in stock, all right? So this is the concentrated solution. So that means that this is MC. And suppose you want to prepare 150 milliliters. Well, that's how much you're going to make. So that's the volume of, yes, of the diluted solution. Suppose you want to prepare 150 milliliters of a sucrose solution, so that's 0.050 molar. Also notice this number is way less. Okay, the smaller one has to be the diluted solution, right? So this has to be MD. And so how many milliliters of the stock solution are needed? The stock solution, again, is the concentrated solution. So that's VC is what you're solving for. So I would divide both sides by MC and take MdVd over MC. And then be very careful when you plug in, because you have two different molarities here. And if you reverse them, then you're going to get the problem wrong. Times 1 time. Yeah, see, I get confused too. I have to look and think about it again. So that if you get 50 milliliters. Yeah. Now I walked around the room and somebody did it wrong and got 450 when they reversed these two. Now that makes absolutely no sense. How are you going to fit 450 milliliters in a 150 milliliter flask? So that tells you right there that that can't be right. It has to make sense. So think about it as you're going along. All right. I'm going to give out the quiz. So we have plenty of time. So first row, first seat, third seat, please line yourselves up so that I don't have to go crazy with the, get right behind, directly behind one another. Every other seat going across. I have different things to give out. I'll give the quiz out first, then I'll come back and I'll do the handouts. Yeah. I'm giving you a nice orange one. If you haven't gotten your ion special problem back, it's still a minute to look at it.
I have this. Do you want it now or should we?
What?
This was, you said we could hand this in for extra.
Yeah, you're supposed to hand it in last time.
Oh, I didn't have it done. I did it for home.
Well, I mean, I posted it on the, what do you call it? But I'll take it. I posted the answers.
Or I guess I shouldn't take this.
Are you sure?
The name on it. Oh. Hi.
Kind of my first time taking an test. I scheduled it for tomorrow.
Are you Sheila?
Thank you so much.
Tomorrow?
Yeah, because
that's fine. Just go.
I can just leave.
Yes. Okay. You're Sheila, right?
Yeah.
I already sent it to them.
Yeah, I wasn't. I've never done this before, so I wasn't sure if I was supposed to like stay here.
No, go.
Thank you.
You have to go to the disability services. I'll take your test.
Well, Are you get these, give these to her? You guys are a little zigzaggy. I'll come around with the scrap paper. What? You didn't get a quiz? Oh, come and get it, okay? Sorry. Got it. Oh, I'm gonna give one out. Oh. Go on to another problem. Anyone in the back need a purple sheet? Good. Back after. I'm pretty sure you didn't have a, yeah, so I'm gonna come around and scratch paper. No, I prefer you didn't write on it. I mean, if you do, it's okay. I just won't use it again. Yeah, if you really want to. I'm gonna come around with scrap paper. So if you want scrap paper, just raise your hand as I come by. Yeah, version 2, problem 1. Version 2, problem 1 says quiz 2B2 under it says blank for moles, just change the moles to grams. I asked you for grams and give you grams. I must probably change it.
I'm sorry, can you repeat that?
Yeah, let me see.
I
Look on
apologize.
top of your paper. It says quiz 2B2. The first question, it asks you for a number of grams. But the blank has moles. Just change that moles to grams, okay? Write the final answer. Anybody wants gravity? Just put the formula, you don't have to put the charges. This is called finance. Oh, they're extra periodic tables somewhere.